Hey guys, hello everyone. So we are going to move onwards to our next topic, that is name reaction, and it is quite related to organic reagents also. So you won't know when you end organic reagents and when you start name reaction. These are like very mixed topics. But if you remember a few name reactions which I have already discussed in some videos, both on my channel as well as on Rasayan Academy app. So you must know what we are talking about. All right. So this is the best way to practice. Let's start the discussion. Now, first question is over here. What is going to be the correct answer when this molecule reacts with TiCl3 in the presence of a zinc copper couple? All right. Yeah. Try doing this by yourself. Stop the video. Do it by yourself. All right. So basically, what kind of a reagent is this? Looks like it is only a reducing agent or something. It is actually a single electron transferring agent. All right. That is, it is going to only give electrons to this system. Who is going to accept these electrons? The double bond? No. The carbonyls. There are two carbonyls which are like very close to each other because of the molecule, because of the symmetry of the molecule. So what we are going to see is, let's say there is a aldehyde group over here and another aldehyde group over here. These are like in a close proximity, not very close but not very far away. All right. So this TiCl3 is going to give you one electron each to these carbonyls, and then they are going to become O minus because this is like a radical anion. All right, now what is going to happen? Since they are close to each other, a bond is going to form in between them. All right, and the titanium over here is going to, titanium becomes 2 plus now, it is going to connect with both of these. Okay, and that is what makes them even closer. Once the electron is given by titanium, it is going to become titanium 2 plus and bind with both of the oxygen. So the carbons now join. Now what happens is, yeah, definitely there are other groups. What happens is, we are just going to see, this is like a pinacol formation because we form the pinacol in same way, but instead of titanium we provide magnesium. All right, but here what does the titanium do? It not only provides this kind of electron, it also takes away the oxygen. So it is actually going to just take away the oxygen and become titanium TiO2, titanium dioxide, and what remains is this, that is, you are like getting a dehydrated या फिर a deoxygenated pinacol. ऐसा लग रहा है क्योंकि pinacol में diol होता है. So from here if we hydrolyze, we are going to get a diol. But here McMurray coupling usually gives you a dehydrated product. But you know what is happening over here? Here we don't see such thing. यहाँ पे एक product बना है which is giving you a double bond, which is actually cis. This is a cis double bond. What about over here? This is a diol. All right, cis diol. This is correct. It is, if it forms, it is going to be a cis diol only. And this is a trans diol. No possibility. So there are two possibilities: option number B or option number C. All right, which one is the correct answer? So guys, what happens is, when you are having, here the temperature is not mentioned, but still whenever you are doing the McMurray coupling, when you realize that titanium is present, it will not end up with the diol. It is going to take away the oxygen in the form of TiO2, and it is going to give you option number B as the correct answer. Alright, so it is always going to give you the alkene, and this particular reaction, McMurray coupling, is used for such kind of cyclization in big molecules also, where two carbonyls are present. Just do the cyclization. It is very frequently. All right, very nice and very easy, not too scary, very simple. The molecules are very big, but the reaction is very simple. Next, what is the major product over here? So guys, by now you must be able to answer these kind of questions very easily. Yes, very simple. Try this out. Okay. So, as I see sodium hydride, carbon disulfide, methyl iodide, what do I do? You know, if you have studied the name reactions, you will know this sodium hydride is a base. It is H minus. This H minus is going to pick out this proton H plus, then it becomes O minus. That O minus is going to attack over this carbon. One of the bond opens up and attacks over methyl. So I'm just directly writing the xanthate. Yes, isn't it? It is going to give you the xanthate ester like this. Now this xanthate can undergo many reactions, but based on the reagent which is used, what is this? It is a combination of TBTH and AIBN. All right, you know what is TBTH and AIBN if you have gone through the radical practice session, right? Reactive intermediates. Now, what is it going to do? It is going to generate a tributyl tin radical which attacks over here on this sulfur. The bonds open up in this way and there is a radical that you get. Now you know. Okay, so everything is very simple. The rest of the molecule is as it is. You get one radical over here. There is no further reaction within the molecule because you have a hydrogen source. Okay, it is going to just grab a hydrogen from over here and it gives you your final product. Deoxygenation. There is no hydroxy group anymore and it is not CH3 because I'm not doing any deprotection over here. So D is the correct answer. What is this reaction? McCombie. Barton-McCombie deoxygenation. All right. I hope that you're liking this. Let's move onwards. Now, next easy question. Very easy. Yes, try this out. The molecules might seem very big, but the answer is very simple. Okay, so what's going on? In the first step, you see that there is H2SO4 and light. So if I'm providing H2SO4, there are two amine molecules which can take up the proton, either this one or this one, right? So let's assume both of these are taking the protons. So they will get a positive charge like this. This is also going to get a positive charge. But what happens is, in the presence of light, only this amine is going to break this nitrogen and halogen bond homolytically. That is going to be a homolytic fission, alright? Yes, remember that. This is a CH2H. I'm writing it like this, okay, deliberately. Now, what do you have? NHME positive radical because already the positive charge is there and one bond breaks in a homolytic manner. So it is going to give you a radical only. Alright, now this radical is also going to take up a hydrogen radical. Yes, from where? From the delta position, alpha, beta, gamma, delta. From this delta position, I've only written the half part of the molecule. ऐसे लिख देते हैं चलो 5 membered only. Now this becomes CH2 radical. This becomes NME. Oh, sorry, I just ate one carbon. Yeah, there's one methyl. There is this NHHME positive in this way. And this CH2 is now going to, because there's one Cl radical also, so this is going to connect with that Cl. This is how it is going to be. So this is the final product of the first step. What did we do? We just formed radicals which did the delta hydrogen abstraction. Alright, now next step you are having a base. What is the base going to do? The base is going to take away one of the hydrogens over here so that the amine becomes neutral. Alright, so that the amines will become neutral and it is N HME, no positive anymore. What is this? CH2Cl. So what are the chances now? Definitely the amine is going to attack over this methyl, isn't it? And definitely it's going to form a 5-member ring. Yeah, मैंने इसको सरका दिया है फिर से. This CH2 is going to be on the this carbon. A little bit tricky this question is, because you have to take care of the places where the groups are attached. See, very close proximity. That is why the SN2 reaction is bound to happen. And it is going to give you option number D over here. Got it? It is option number B also looks very similar. What's wrong with option number B? Yeah, I think it is the same thing only. Yeah, option B and D are same. So basically, this is Hoffman-Loeffler-Freytag reaction. All right, Hoffman-Loeffler-Freytag. If you haven't studied, please do. All right, guys. So now we are going to move onwards, and we are going to see this question over here. It's a very simple one. Just first try doing this, and eventually we are going to discuss the answer. Alright, so basically what's happening over here, sodium is there to provide electrons to these carbonyls like this, and after providing the electrons, the ethoxy are going to eliminate. When the ethoxy eliminates, I hope that you have recognized this reaction, because you have seen this plenty of times now. Both of these are going to be radical on the carbonyl carbon, and that's why it is going to connect from over here. After connecting, there is going to be a connection like this. After connecting, these are still carbonyls. Alright, so the sodium can still provide electrons to the system. It becomes O minus now, and this also becomes O minus, and one electron sodium gives to each of the carbonyl. That's why it becomes a double bond. So this is exactly what we see in the acylone reaction. Alright, we have seen this already yesterday. Now the thing is, it is going to be fixed as SiMe3, because here you are going to have the oxygen which is protected by this. Now we don't have aqueous workup. It is only one-step reaction. Even though the final product after hydrolysis should be option number C, but we don't have hydrolysis. That's why we have to say B is the correct answer. Alright, let's move onwards. Next question. Again, stop the video, do it by yourself. Alright, so you must have figured out, guys, it's a very simple one. First one is nothing but Birch reduction. It is Birch reduction, and in the Birch reduction, you know that these are electron donating groups, and this carbonyl over here is an electron withdrawing group. So what is going to happen? The electron is going to be transferred in such a way that it attacks, it does not disturb the electron withdrawing donating group, and puts the electron density in the electron withdrawing group only. So that's why the whole molecule is now going to be written like this. Okay, the radical comes over here. Now sodium is going to give more radical onto this carbon, and after complete reduction it is going to look like this. Why is the other carbon not reduced over here? Usually 1,4 reduction takes place in the Birch reduction, but this part is already very electron rich. That's why the electron won't go over there. So what happens is, after the Birch reduction is carried out on this carbon now, in the second step you have added the electrophile, that is ethyl iodide. So now the electrophile is going to be attacked by the electron density on this carbon. Alright, so the ethyl group is going to come up over here, and B is going to be the correct answer. Alright, this is how it is going to be. Not A, not D, because this is not the correct regio selectivity. Only option B is going to be the correct answer. Let's move onwards to another important question, question number 6. All right, this is the most repeated question in all of the competitive exams because ये काफी common name reaction है. So try doing this on your own and then we'll discuss the answer. So basically guys, this is nothing but the Eschen-Mosher fragmentation. I hope that you have studied this reaction. It is a very simple reaction. First of all, the peroxide is going to attack over here and it's going to do the epoxidation. Since this is a electron deficient alkene, you cannot take metachloroperbenzoic acid for epoxidation. That is why you are going to need nucleophilic reagent for the epoxidation. Alright, so after that, the second step is going to be like this, just the conversion of this molecule into a hydrazone. Now, in the presence of base, it is a methoxy base, the proton is going to be eliminated in this way. Like this, and the epoxide is opened up. Alright, what happens next? Now, next is the step of fragmentation. The alright, there is a double bond. Okay, so fragmentation happens in this way and is driven entropically. Alright, so fragmentation happens because in this process, one molecule gives rise to 3 different molecules. Okay, this plus the nitrogen plus the TS minus. That's why it is entropically very favored. This is your correct answer, and it's a Eschen-Mosher fragmentation reaction which is asked almost every year. Next, what is going to be the major product in this reaction? Yes guys, try to stop the video and do it by yourself. Okay, so you know about the Gilman's reagent. When you have studied the organometallic reagents, you will know Gilman's reagent, where methyl is a soft base or a soft nucleophile, is going to do a conjugate addition, conjugate attack. That is the 1,4 addition onto this alpha beta unsaturated carbonyl system. So the methyl is going to attack over here. This is how the bond is going to open up, and it gives you something like this. Also, since there is an isopropyl group which is present below, methyl has attacked above. Now it is going to fall back and simply attack over this carbon. Br minus is going to eliminate. That is going to give you option number A as the major product, because since one methyl is already above, this bond definitely has to go below, and that is going to favor the cyclization taking place from below and this methyl coming up. Alright, so cis geometry is going to be more favored, and that's why A is the correct answer. Moving onwards to next question, what is the major product over here? Alright guys, so we see that where tin is present and palladium is present, along with the aryl, we cannot say halide, but it's a triflate, which is a good leaving group. The same mechanism is going to be followed as any other coupling reaction. So whenever tin is present, you can say that this is going to be a Stille coupling reaction. Alright, now the most important part is you are going to take palladium and do the same mechanism, oxidative addition, transmetallation, followed by reductive elimination. And since we can also see a carbonyl, that is going to be one more step, that is the migratory insertion of the bonds with the carbonyl. Alright, so what we usually expect is after doing the oxidative addition as well as the transmetallation, the molecule is going to look like this. Alright, this is how the molecule is going to be. But since we also have a carbonyl over here, it is not directly going to be a reductive elimination, but reductive elimination and insertion of oxygen together. That's why the product is going to be like this, which is option number B. So it is a very simple reaction. You are not going to replace silicon in the presence of tin, so that's why A is wrong. C and D are wrong because they are missing out on a lot of groups. So answer is option number B, and it's simply still a coupling reaction. Moving onwards, what is the major product in this reaction? Stop the video, try it on your own, very simple. Alright guys, so in the presence of H2SO4, definitely this OH molecule is going to convert into hydronium ion and want to leave. After it leaves, the double bond is going to shift over here and forms a carbocation. Now this carbocation is going to be stabilized by furan since the attack is going to take place from the third position. That gives rise to a formation of a 6-membered ring on this side, and this carbon and this carbon, and this one, yeah, both of these are connected to the same carbocation carbon. That means it is going to give you a spiro compound like this, and oxygen still has a positive charge. It is not going to end up like this because after the aromatization, it is finally going to give you option number C. It is going to regain aromaticity because there is a proton to lose. So it's not going to be like option number A. These are absurd because it is going to be a spiro compound, and D is also wrong. Okay, you cannot have the reaction taking place from any other center in case of furan. Electrophilic aromatic substitution in furan when the second position is occupied cannot take place from fifth one because it is too far away. Alright, so it is the answer C. Next good question, what is the major product over here? Again guys, stop the video, do it by yourself. This is a very, very important and interesting reaction. So whenever you see compounds like this, these are known as sulfones. Alright, whenever you have S double bond O, that is a sulfoxide, and when you don't have any oxygen, that is known as sulfide. Okay, so this butyl lithium definitely is going to remove a proton from the alpha position of the sulfone because it is like a double of a carbonyl. A carbonyl makes the alpha proton acidic, and this is like the double of a carbonyl, so definitely it is going to make this acidic also. Has a negative charge that attacks in the second part of the molecule question. You have ethyl aldehyde in this way. Now here the carbon is going to attack, and after that you have to connect two of these molecules, SO2PH, CHET O minus, and usually we have acetic anhydride AC2O. So either you get PHCOCl or AC2O. The purpose of these is only to stabilize the O minus and form OCOPH or acetate, whichever you have. It is going to be like this. Now, one more important thing before we do the fourth step, that is the molecule is going to rearrange because these groups are so bulky. The molecule is going to rearrange itself such that the bulky groups are away from each other. Okay, and now I'm going to do the last step, that is the reduction by sodium amalgam. Now sodium amalgam, sodium has the tendency to give electrons. Where is it going to give electrons? You have a carbonyl over here, you have a sulfonyl over here, but definitely sulfonyl is more electron deficient because sulfur is there in +6 oxidation state, being an electronegative atom. So this electron transferred over sulfur opens up the epoxide opens up the oxide double bond O bond. CHET OCOPH as it is, nothing has changed. And here you have an O minus, a pH, and a double bond O. Now there is also a radical on sulfur. What happens next? Next is this radical is going to fall over. You know, the oxygen already has electron density, so it is going to fall over and the bond is going to open up on this side, such that you are going to get an alkene because there is definitely a good leaving group present. That is the OCOPH. Now this is going to be the leaving group, and this is also the leaving group where sulfur has got radicals or the free electrons. So A is going to be the correct answer. This whole reaction, it is Julia Lithgow olefination, and it has one more variant which is known as a Julia Kochinsky reaction. And in this reaction, this is important because it has E selectivity of the products. E selectivity. That is, more stable products are formed. Alright, in the case of alkenes. Here both of these groups are same, so we cannot decide, but yeah, it does.